All righty, folks. Okay, day 4 of 6 here of limits. And again, like I said before, we're not covering everything you would cover in your first unit of limits in calculus. We're covering maybe about 80 to 85% of it. So we're covering a lot of it, not quite the whole thing, but quite a bit of it. So the next thing we're going to look at is something called one-sided limits. Now, one-sided limits are limits that deal with either limits from the negative side or limits that come from the positive side. Now, one of the reasons why they call them negative limits is because if they're coming from the left, that means they're coming from negative infinity. So the limit's coming from the left-hand side. They call it positive from the positive side, the right side, because that's where positive infinity is. And so it's coming from the right side. So when you're seeing these limits from the left side or the right side, don't realize they're coming from negative and positive infinity. So that's why negative it goes with left, positive goes with right. So let's see if we can't talk a little bit more about this. So this says the limit as x approaches a from the negative side or from the left side of f of x equals m. In other words, notice where a is on our graph here. Let's see, I need this right here. Notice, can approach a from the left side and it can approach a from the right side. But if I tell you specifically that I want it from the negative side or the left side, then that means this right here, I don't care about that. I only care about the value on the left-hand side. Likewise, when we see the positive side, even though it approaches a down here from the left side and right here from the right side, I only want it from the positive infinity side. So therefore, I only want just that right side. So that means this goes away. The negative side means it's coming from negative infinity, the left-hand side. The positive here means it's coming from positive infinity or the right side. So now in order for limits to exist, the two sides end up having to be equal. So we would say that the limit doesn't exist at a as x approaches a because the two one-sided limits don't equal each other. They don't agree. And in fact, that's one of our famous theorems here. We call it the existence of a limit theorem. In order for a limit to exist, it has to be equal to the same thing on both the left side and the right side. So, in other words, in order for a limit to exist, the left side and the right-sided limits, they both have to be equal to the same value. If that's the case, then the limit itself exists and the limit at x equals that. Now I could find one-sided limits even though the regular limit doesn't work, because a one-sided limit doesn't require the regular side to work. So for instance, if I'm coming at x equals 1, like we are talking about here in this problem, I have approaching 1 from the right side, but I also have approaching 1 from the left side. So if I'm asking you to tell me what it is at 1, let's use an arrow for that. Smaller as well. So if I'm asking you to tell me what is x equals at 1, I'm saying as we go up, what value is it looking like? So the negative value, if I'm going from the negative side, this is the left side. So the arrow, so the graph on the left side, it's coming towards 2. And then if I'm coming from the positive side, that's the right side. And so that'd be the graph coming from up to 3. Now, in order for my limit to exist, I need to have it'd be the same thing on both sides. So I would say here, as far as the limit as x of 1 approaches 0, first of all, I'd get rid of that equal sign because it isn't equals. And I would say that the limit does not exist because, and the reason why it doesn't exist is because the limit as x approaches 1 from the left side, a lot of people forget to put the f of x here. I always have to dock when, in calculus when people forget the f of x, doesn't equal 1 from the right side. In order for the limit to exist, these two functions, these two one-sided limits, the 2 and the 3, have to be the same value. And if they're the same value, then that means at 1 itself it equals the same value. So I can find one-sided limits, but that doesn't mean that I can find the actual whole limit itself. So let's keep going a little bit. So how about we deal with finding out some one-sided limits? Notice when x is less than, so general rule, when x is less than, that would be from the left side or from the negative side. When we are dealing with greater than, that's going to be from the right side or from the positive side. So here we go. Limit from 1 from the negative side of f of x. So that means we're going to be using this function right here. Pi of x over 2 plus 3. And that equals, when I plug 1 in, so you just literally just plug 1 in there. We don't bring the negative in with us when we plug it in. So pi times 1, we don't put 1 to the negative side when we plug it in. We just plug the 1 in, plus 3. So sine of pi over 2 plus 3 is the same thing as 1 plus 3. So it is 4. So from the negative side, my limit would be equal to 4. From the positive side, notice I'm not asking you which one, I'm not asking you for the function value. I'm asking you only for the limit. So which one does it get really close to? So as we approach from the positive side, and that would be the greater side. So we plug it in there. Again, notice I'm not plugging the plus in with the 1. It's just 1. So that'd be 1 plus 2 equals 3. So notice the one side limit is 4. The other one side limit is 3. That means that the actual limit itself, does not exist. Because the one-sided limits are not equal to each other. All right, so with this in mind, why don't you guys go ahead and try the next one? So go ahead and pause the video and see what you guys can come up with on this next piecewise function using one-sided limits. Go for it. All right, let's see how you did. The negative side, that would be the less than side. So we're going to plug it in there into the x plus 5 minus 2. So the square root of 4 plus 5, that's 9, so that equals 3 minus 2, that equals 1. And then the positive side, that's when it's greater than. So we have 3 minus x plus 2 over 3. So 3 minus 4 plus 2 over 3. So 3 minus 2 would be equal to 1. So it turns out they both are the same. Since they're both the same, that means that the limit itself is equal to 1 because, and I got to say why, because the two one-sided limits are equal. And not just equal, but they both equal 1. All right. So hopefully we have the idea about one-sided limits and whether or not limits exist or not. And if we can do that, then we can get into the real technical final thing, our technical definition of continuity, of determining if something is continuous at a point. For instance, in order to be continuous at a point, it has to have three things. First of all, the function must be defined. The function must be defined. So for instance, here at 2, notice f of negative 2 is defined. It's a solid dot and it equals 2. On top of that, the limit has to exist. So if we look here at 2, notice the left side and the right side both go to 2. So the limit would exist and it would be equal to 2. And not just that, the limit value would be equal to the function value. If that isn't the case, if one of those three things is broken, then our function isn't continuous. For instance, look at negative 5 here. F of negative 5 equals 3. But the limit for it, the limit exists, it just happens to go to a different value. It goes to 7. But since these two values aren't the same, the function wouldn't be continuous at that point. For instance, take a look at this one right here, over at 4. There is no function value defined, and so although the limit exists at 4, f of 4 isn't defined. So therefore, it'd break down. If you look at this last example here, how about at x equals 1? We have a f of 1, but notice this one, the limit doesn't exist. So therefore, on that one, it wouldn't exist because the limit as f of x approaches 1 does not exist. In order for it to exist, the function value has to be defined, the limit value has to exist, and the function value has to be equal to the limit value like it is here at x equals -2. Again, f of 2 is 2, function, so the function is defined. The limit as x approaches 2 of f of x equals 2. So the limit exists, and on top of that, the limit value has to be equal to the function value in order for it to be continuous at that point. Three things always have to be true in order for a function to be continuous at a certain value of x. So what we're going to do here is we're going to go through and actually prove or verify if a function is continuous. So we'll do one together, and then I'm going to have you guys do one. And we'll call it a day. So let's take this function right here. Is it continuous at x equals 5? The first thing we have to do is we have to figure out, is it defined? So here's my equal sign right there. So f of, I'm going to plug it in here. F of 5 equals 8 minus 5, which is 3. So that means f of 5 is 3. So f of 5 is defined. So we made the first qualification. Now we got to figure out, does the limit exist? So we have to do the two one-sided limits now to figure out, does the limit exist? So we're going to take the negative side, that's the less than side. So we're going to evaluate the radical, so 2x minus 1, which would be equal to 3. So it works there. And I already know that it works on the positive side, but I've still got to show that, even though I've already pretty much done it. So we plug them in. And so the one-side limits are equal. So therefore, I could say that the limit does exist, and I know what the value is. So we're going to do a little writing here. Since the limit from the left side equals 3, which equals the limit from the right side, then that means the limit as x approaches 5 exists. And it equals 3. So that was the second thing. We had to prove that the limit existed. So now we have the function value existing, the limit, I'm sorry, we have the function value defined, we have the limit existing. So the last thing we do is we got to show that they are the same. So since f of 5 equals 3, which equals the limit value then f of x is continuous at x equals 5. So a little bit of writing that we have to do to prove beyond a shadow of a doubt that it actually does work. So now we've just proven at 5, it is in fact continuous. This is the mathematical way to prove things are continuous. So let's let you guys try one yourselves. I'm going to leave our old answer up here while you guys try this one, just so you can use it as an example. So go ahead, pause the video and see if you can try this one. All right, let's see how you guys did here. Let's see if we can't go through and do this together. All right, so we got to figure out, is G defined? So that's going to be 3 times cosine of pi over 2. I'm sorry, pi times 2, so 2 pi plus 4. So cosine of 2 pi is the same thing as cosine of 0, so that's 3 times 1 plus 4. So that means it equals 7. So that means G of 2 is defined. It equals 7. The next thing is the one-sided limits. So we're first going to do it from the left side, the negative side, that's less than. And I've already plugged that in there, so I know that equals 7. Now we're going to go ahead and do it from the right side. So that would be the 3x plus 1 side. That also equals 7. So since they both equal 7, that means the limit exists and it equals 7. So we got to write our statement about that. So since the limit as x approaches 2 from the negative side of g of x equals 7, which equals the limit as x approaches 2 from the right side of g of x, then that means the limit as x approaches 2 of g of x exists and it is equal to 0. Oops, 0, 7. Let's try that instead. All righty, so now we got the limit existing, we've got the function value defined, and now we can finish this up. So since the function value equals 7, which equals the limit value, and what you find out in calculus, and you find the same thing in stats as well, it's not so much about being able to do the problem, it's about being able to explain it. It's the writing that's important. Then g of x is continuous at x equals 2. All right, and that brings us to the end here, friends. So we'll come back tomorrow and we will spend, honestly, we'll spend a little more time with that difference quotient that we learned about yesterday. So I'll see you then.